Hello, everyone. I'm Terry Xu. I'm from Purdue University at Computer Science Department. I'm a fifth-year PhD student working with my advisor, Patrick Exter, and Matthias Payer. So thank you for coming. I'm presenting a joint work with my co-author, Kevin Hoffman, who is a previous PhD student, graduated a couple of years ago, and my advisor, Patrick Exter, and Matthias Payer here. This work is about strict thread isolation for C or C++ multithreaded applications. We published this work at this year's CCS in Vienna, and you're welcome to check out the paper online. So let's get started. So what are the problems of today's software? So today's software have numerous components running within the same process address space. What makes this situation a security nightmare is that some of these software components, they could be developed by various third parties. So if a targeted application is a multi-threaded application, then all of these software components are unconditionally trusted, even if they shouldn't be. So that's the problem here. To provide isolation for software components, one could use process to isolate program data. But that requires the programmer to completely redesign the legacy software. Another popular solution is based on software fault isolation, which could cause various delays due to the software monitor, depending on the implementation techniques. So here we use a really simple example to illustrate the isolation problem in a single process address space. Imagine this green box to be the address space of a program. In this example, the program stores its own secret, and they shouldn't be accessible by other irrelevant software components. But as you all know, the software could load modules, plugins for web browsers to even access the physical devices on your systems, and various libraries, and even microservices. So as the program adds more and more components to the same process address space, it increases the chance of being compromised. So it's a problem. It takes only one component to be compromised to exploit the entire program. This problem is due to the intrinsically shared single process address space and the lack of intra-process isolation. So one could use process to isolate the software components, but process isolation has its own drawbacks. For example, non-trivial IPC increases the code complexity, and sometimes even the performance overhead is observable. Also, there's a lot of resource duplication at system level, and cross-process synchronization can also be a headache for programmers. And most importantly, it is extremely difficult to overhaul programs with large code base to use process isolation. But if we could safely bring all this process address space together, and therefore remove the expensive IPC, programmers will be able to selectively isolate the process memory and have an efficient and secure partially shared memory pool. So the ability to selectively isolate the process memory allows the program to eliminate IPC and to share as many resources as possible at the system level. And the program could assume thread synchronization still works. And because of the shared memory assumption, the code changes could be minimum in terms of memory access and data sharing. So efficient and secure intra-process isolation is the motivation of our work here. Our goal is to provide the programmer with a programming abstraction to selectively isolate process memory with several properties. We believe that in order for security tools to be widely and quickly adapted, a tool needs to be flexible so that no matter the client or the server-side applications can take advantage of it. Second, we think that new tool should be extremely easy to use without the need for a programmer to overhaul the entire legacy software. Also, a tool that does not require hardware modifications or specific hardware means that it is ready to be deployed on today's commodity system. Last but not least, a tool shouldn't sacrifice parallelism when providing security, and it should guarantee the security of the software without serializing execution. So to address these design challenges, we propose secure memory views. We call it SMVs. It allows the programmer to selectively isolate a process address space based on user-defined policy. So we define 3 abstractions to manage process memory to achieve intra-process isolation. First, we define a memory protection domain to be a contiguous range of virtual memory address. Second, we define a secure memory view as a thread container with a collection of memory protection domain. So an SMV defines whether a thread could read, write, execute, or allocate free data in the memory domain. So finally, we create a special thread called SMB thread that strictly follows the privilege defined by SMVs. So here's a high-level overview of what SMVs look like. There are 5 memory domains in this example and 4 SMV threads. And thread T4 is using 2 memory domains, as you can see in this figure. So suppose domain L is compromised by the attacker. So it's marked in red. And this is what the memory domains look like in the program's virtual address space. So the compromised thread T3 is isolated by SMV3 that can only access the memory pages in the memory domain L. So it is not possible for T3 to access memory pages in memory domain S that stores the program secret, even though they are just threads living within the same process address space. Okay, so SMV is really easy to use. The programmer just need to link the SMV library when compiling source code and include a header file. So just to give a really simple example of how to use SMVs with some of the basic API calls. First, we can create a memory domain and store the program secret in that domain. Then we create an SMV container, and we make the SMV join the memory domain. So there's a mapping recording in the system. In order to access data in the memory domain, we need to grant permission to the SMV. So you can see there's a dash line there, and also the privilege recorded at the bottom of the SMV. So here we allow SMV1 to read data in memory domain 1, but nothing else. And finally, we create an SMV thread that is totally isolated by SMV1. Okay, so after the SMV thread finishes its job, then we join the thread. So the thread leaves the system and make the SMV leave the system, and we kill SMV and then kill the memory domain from the system. So this privilege setup might be a little inconvenient in terms of refactoring the legacy software. So we provide an easier way for the programmer to minimize the code refactoring effort. So the SMV API could automatically intercept malloc and pthread create calls and replace them with a set of SMV-related functions. Therefore, the programmer only needs to add 2 lines of code to the program, one for the header and another line of code for initializing the main program. In this library assisted setup, each pthread is automatically intercepted and replaced by an SMV thread, and will receive a private domain for its stack initially. So the programmer could assume that threads are isolated from each other. In addition, thread local memory allocation happens automatically in that thread's private domain that is not accessible by all other threads. So in this case, where threads need to, in the case where threads need to share data, the program could create a shared domain and carefully control the access privilege. So far, we've talked about how to use our proposed SMVs from the user space. We implemented the SMV API in the user space for about 800 lines of code. But what's really managing the memory views and enforcing the memory reference is actually in the kernel space that we implemented with around 2,000 lines of code in our Linux kernel prototype. We've added SMB Kernel Module that acts as system calls to invoke internal kernel function. The SMV metadata management manages the overall per process isolation setup. We also manipulate the page table for threads to isolate their memory space. And we utilize the page fault handler as a software monitor to trap illegal memory references. So dig into the details. In the current Linux kernel, each process has one struct. Here, struct, the means memory management in kernel, in Linux kernel. So the struct describes the memory space of a process. A process child thread use the same struct so that they are seeing the exact same virtual memory space and with the same permission. For metadata management, we added several data structures to record a per process isolation setup in the kernel space. The most important ones are mdom struct and SMB struct. They record the privilege setup and virtual address mapping with privilege information inside the kernel so that the attacker cannot bypass kernel level protection to crack SMB's design. It has to exploit kernel in order to attack SMBs. So you will notice each SMB uses one page table. So we describe how we separate the page table in the next slide. This is how the original Linux kernel manages a process and its threads memory space. So you can see there, in this example, there are 3 threads. They're all sharing the same page table and all the memory management related metadata. But in SMBs, we don't want threads to have global access to the entire process address space. Therefore, we need to separate their page tables. All threads should mutually agree on the process address space. But with different page tables, threads are actually seeing the same virtual memory space, but with different permissions. So with this memory management, we could allow thread 1 to read and write to the protected region. And thread 2 could only read, while thread 3 has no permission at all. So this partially shared memory space has several benefits. For example, it allows legacy thread synchronization that utilizes struct to work with SMB seamlessly. If you use pthreads library, most of the pthreads API calls, when they are calling the synchronization APIs internally, Linux kernel uses this struct. It also allows debugging tools such as Valgrind to attach to an SMB program because we don't use clone syscall to create different process address space, which breaks the single process address space assumption for tools like Valgrind. And most importantly, we found that sharing the same struct could avoid many kernel synchronization for related data structures. Okay, so once we have threads page table set up separately, we can check the access privilege when a page fault happens. So when handling a page fault, the original Linux kernel only checks whether a memory access is valid by determining if a given memory area is mapped in the system. If a region is not mapped, a segmentation fault signal will be delivered to the program and that triggered a page fault. If an access memory region is mapped or fixable, and the kernel will proceed to prepare the memory page, and the same instruction is executed again without the segfault signal. So to facilitate intra-process isolation, we added additional privilege checks just before the kernel actually proceed to fix the page fault. So the added privilege checks are marked in a gray box. Our privilege checks first make sure the thread type. If the fault is generated by an SMB thread, it further checks whether the SMB thread is running in the SMB that has the privilege to access the domain containing the fault address. If the page fault passes all checks, then the SMB kernel will perform domain paging to fix the page fault. Otherwise, the SMB kernel will send segmentation fault signal to the faulty SMB thread to block underprivileged access. So that's all for a high-level implementation. So now we go to evaluation. We evaluated our SMB's prototype on Intel machine with 4 cores. and 16 gigabytes of RAM running our modified Linux kernel based on pretty recent version released early this year. We compile all the benchmarks into two versions, pthreads and SMB threads. For all the multi-threaded benchmarks, we created n+1 protection domains, where n is the number of threads, and the additional memory domain is the global pool for threads to securely share data. To make sure our modification doesn't break the Linux kernel's correctness, we tested our SMB kernel with a set of testing scripts in Linux test project. I didn't observe any system errors or kernel panic. So it's just basically a set of script that is smashing all the workload to your kernel and see if your kernel crashes or didn't pass any test case, or your kernel will, sometimes in most of the case, your kernel will have kernel panic if your memory pages is not set up correctly. So we passed all that checks. The benchmark we used are Parsec, Firefox web browser, Cherokee, and Apache Web Service. So all this experiment can be reproduced on systems running on today's x86 hardware. So first we look at Parsec, which includes 12 applications in different application domains. For example, machine learning, compression, decompression, and graphics kind of workloads. These applications are all multi-threaded with pretty complex thread interaction and memory operations. Although it is not necessary to protect the security of this benchmark application because they are just benchmark program without program secret, but we used Parsec to show that SMB can protect threads private stack for different applications with intensive and parallel memory operations. So there are 12 benchmarks, and the last bar is the average overhead. The overall performance overhead is around 2%, and we only added about 2 lines of code to each of the benchmark. So to test real-world applications, we first look at multi-threaded web servers. We chose Cherokee because it uses per-thread memory buffer to isolate threads from remote connections. The SMB version of the server is able to automatically handle thread isolation with only 2 lines of code changes, 1 line for header and another one for initializing the main program. The server has 40 threads by default to handle incoming requests concurrently. We use standard Apache Bench to send 100,000 requests with concurrency levels up to 4 and measure the runtime overhead. So the results suggest that the security-enhanced Cherokee server does not incur more than 1% of runtime overhead in all cases. We also ran experiments with Apache Web Server with even larger files, up to 1 gigabyte, and the overhead stays below 1%. Finally, we look at whether SMB will work on practical and more complex software, such as web browsers that require strong resource isolation. We use SMBs to protect Firefox JavaScript engine. It's called SpiderMonkey. The original Firefox already isolates resource for different tabs using the concept of compartments. But the isolation boundaries for these compartments are only logical, meaning that if there is a memory bug, then the attacker can exploit that memory bug and then attack other compartments. It's still possible. So we introduced a new thread type called SMB thread to Firefox with around 12 lines of code changes so that JavaScript engine could isolate jobs for different compartments. So we ran these 4 different JavaScript benchmarks available online. You can run this benchmark online to use your browser, Safari or Chrome. And we ran these benchmarks and I measured the runtime overhead. Each benchmark contains about 20 to 40 workloads. These benchmarks are designed to be run in its own tab, and the page faults are trapped by SMBs to check the thread's access privilege. So the overall result indicates that the performance overhead is about 2%. It's about 2% on average. So we believe our prototype could be practical for production software like Firefox. So there are some limitations and concerns surrounding the current prototype of SMVs. For example, SMVs do not protect against malicious library threats. So to overcome this issue, the programmer could obtain library source code and then compile it with SMVs for maximum protection. Second, SMVs provide intra-process isolation, but have to trust the OS kernel. There are several orthogonal works that could be used to further isolate the OS kernel. For example, nested kernel for x86 architecture or SCI on ARM for mobile devices. Also, currently, SMVs do not protect against attacks targeting data on the same page. This problem could be handled by avoiding poor data placement. For example, don't put program secrets right next to an attacker-controlled payload in the same page. And finally, SMVs cannot guard system with hardware bugs. They will affect the correctness of the page table bits. We have some interesting ideas for our ongoing work. Just to name a few, we envision a secure context switch mechanism that allows SMV threads to securely switch between different SMVs. Such mechanism will help applications to that embedded privileged component into underprivileged one in the same process space to isolate the memory views. For example, serverless database applications such as SQLite 3 or Tokyo Cabinet. In addition, we're also looking at mechanism for SMVs across different process address spaces to collaborate in a secure and controlled fashion. So this will provide software almost unbounded amount of virtual memory with capabilities protection. Finally, SMVs rely on the correctness of isolation setup to provide protection. Therefore, we are interested in designing a practical tool that will guide the programmer to design secure computing environment. Okay, to summarize, we propose a programming abstraction with kernel level implementation called SMVs for intra-process isolation. SMVs allow the programmer to selectively isolate process memory for threads so that a malicious fault domain cannot compromise other benign ones. We believe SMVs are flexible and easy to use. It's flexible as we've shown that we were able to use SMVs on different software from desktop web browser to backend web servers. It's easy to use because the evaluation showed that the SMVs require at most 12 lines of code changes to legacy software such as Firefox with 13 million lines of code. SMVs rely on commodity hardware, so no FPGA or special hardware is needed. Lastly, the system's low runtime overhead in various benchmarks and real-world applications to show that this protection mechanism could become a fairly practical solution for intra-process isolation. That concludes my talk. The SMV's prototype is publicly available on GitHub. You're welcome to try the system out, and I'm sure the prototype is not perfect. So feel free to contact me if you have interesting ideas on how to improve the prototype or any spin-off projects. Thank you. I'll take questions. Any questions?
I have a question. Could you go in more details? How do you enforce those policies?
So the policy is defined by the programmer. So the programmer has to say, okay, I have this set of virtual memory region, and then I allow only set of threads to access those regions. So it's set up by the programmer at the high level, but the privilege enforcement is implemented in the kernel level. So this is the architecture. So you can use API calls. As a programmer, you can use our API calls to insert the policy setup in your source code and then compile it with our library. And then you run the program on our kernel. Whenever there's a security violation, the kernel will intercept that violation through page fault. Yes?
So where is this SMB is located around the kernel?
So there are two parts. One part is user level library, and there is another part that's sitting inside the kernel. So as you can see in this our architecture figure, so I have user level. There's user level, a user SMB user space API. So those are the APIs the programmer uses to set up the security policy. And after that, all the secure access enforcement is done by the kernel, which is located in the kernel space, and the programmer has no privilege to touch those.
So if an attacker wants to attack, he has to,
Go to the kernel space.
which is kind of,
I wouldn't say it's not possible. It is possible because there are a lot of kernel exploits existing in today's attack. I wouldn't say it's hard either. I would say it's an orthogonal topic. You can use other protection mechanism and then combine that with SMBs to provide full protection. Yeah. Are there other questions? All right, thank you.